Hello, hi everyone. Welcome to CS460. Okay, so my name is Yang Xu, and I am an assistant professor in computer science department. And this is my actually fourth semester teaching algorithms and their analysis. Okay, and I see a question in the chat. So right now on the canvas, there are two sections. I think most of you are in section 1, but there's another section 3, right? So it's a question here. I have uploaded the course content, the slides, the syllabus to section 1. And for section 3, I'm sorry, I didn't do that because the sessions gonna be merged together. The two sessions will be merged, and by that time, you will be able to see all the slides, everything else. And I'm going to place the merge request today, and I think latest time by tomorrow it should be already done. Yeah, that's how the course selection system goes. And sorry for the inconvenience. Let me see. Okay, already 61 persons in the channel. Okay, so this is our first class for this semester, and I have several slides prepared going through the course outline. We're going to talk about assignments, exams, quizzes, and there's an intro about why we need to study algorithms and why is it important. And we're going to go through a simple example showing that the more we know about algorithms actually can sometimes save us time, save us money, and it is actually a kind of you can think of it as soft assets in computational systems. All right. Yeah, so let me get started on the slides. First of all, about the course, this is an upper division course, and it emphasizes on analyzing and solving algorithm problems. So as the learning goal for this course, we will after this course for this semester is done, we will need to understand a broad range of different families of algorithms. And here, what I listed here is the several main categories, or what we call families of algorithms: divide and conquer, and it is one of the most common types. That's type of algorithm that solves pretty common problems, real-world problems. Okay, and it is closely related to the dynamic programming approach, but also the differences is in a problem per se. But it's interesting to see the differences between these two categories, and we'll need to tell when to apply which kind of algorithms. And also the third type, greedy, it's also kind of related to the divide and conquer and the dynamic programming approach. Well, I would say it's more related to the dynamic programming approach, but with some simplification. Okay? And graph is a big category of algorithms that covers a complex data structure called graph. Okay, and so we're gonna spend quite amount of time on the graph algorithm. Okay. But other than that, for this semester, we are also going to step into several basic data structures like binary search trees. And in order to fully introduce all the implementing details, we will also look at stacks and queues, priority queues. I believe these contents are already covered in one of the prerequisites in the data structure course. Okay, so other than that, there's another special type of data structure called hash table. Okay, that will be one of the chapters in this semester. Okay, so this hash table data structure together with the hash functions, this topic relates to one of the most popular areas in computer science, which is cryptography. Okay, which is the founding fundamental basis for the very hot crypto business area, right? So we're gonna look at touch a little bit about the hash functions for the basic hash table and a little bit about the crypto hash. So crypto hash is a different hash function with the regular hash functions, but we're gonna touch a little bit about that. Okay, so there's a question that do we need to review the old algorithms data structures or we will review them here? I don't think you need to review everything in data structure. So because first of all, we're going to introduce the algorithms with two sorting algorithms. Okay, we're going to introduce insert and sort and merge sort. So if you had a chance to look at these two algorithms, you may have already had some experience about that, about these two algorithms in data structure course, but we're gonna, build the algorithms from scratch through the lecture, and also there will be a programming-based assignments that help you go through the processes. So I don't think there's a need to go through the old data structure textbooks. Yeah, but there's indeed some connections to data structures, actually very close connections. All right, next, the second goal is we're gonna know the technique to describe and analyze the performance of algorithms, which is the asymptotic notation. Sometimes it goes by the big O notation, big theta, and the big omega notations. So these are the kind of the universal language to describe the running time of an algorithm, the memory cost of an algorithm. Okay, we're gonna know about the mathematical definition of those big O, big omega, and big theta notations, and we'll study cases where and how these notations will be applied. All right. So lastly, after the course, we have gone through the whole course. We wish you to have the capability of knowing several different solutions for maybe one of the problems. Okay, one of the most common problems in real world scenarios like search, like sorting. You should be able to realize the existence of different solutions, and actually you can know how to implement, how to choose the most optimal solutions based on different conditions. Okay. All right, as I said, we have prerequisites of data structure and also linear algebra. Okay, that's a little bit about the course and the goals, the learning outcomes. Yeah, so I see a question about prerequisites. I think it's okay if you are taking 254 together with 460. That's okay. Yeah. But I would worry a little bit if you don't have data structure already taken. Okay. So here comes the textbook. We will use Corman's Introduction to Algorithms, MIT Press. It's a 3rd edition. So it's a very good book, thick, okay, very verbose, a lot of details, math, and very detailed explanations for algorithms, okay. How I organize the contents in my slides is basically based on the textbook, okay. So for before each lecture, I will usually I will put a notes in Canvas that you need to read several pages in the corresponding part of the textbook, okay. And in the slides, I will also put a notes somewhere that's maybe some details of the proof, or maybe some of the details of the algorithm are neglected, and you will be encouraged to refer to the book to get the full details. Okay. Right. But for preparing examples, for preparing exams, for example, I think using the lecture slides that I'm going to upload before each lecture in the future, it'll be already sufficient to cover all the topics, okay? But as I said, reading the book will be really helpful. Okay, yeah, you don't need to buy a paper-based book because there is several online versions available online here that you can get for free. All right. So yeah, next points, it's an important point. For this course, there's no prior knowledge, required prior knowledge on programming languages or preferences over which programming language we should use. Okay. But if you do know Python, Java, or C, or other modern languages, it will be a plus, okay? Because there will be 2 types of assignments. First, we will have a paper-based question set, okay? And the number of sets is usually around 5 to 6 for the syllabus. For this semester, I put 6 question sets in there, if I remember correctly, okay? And each question set consists of 5 to 6 small questions, okay, that require you to work on papers, okay? So for the paper-based questions, it could be like you prove some mathematical concepts, or you write down the pseudocode to implementing certain algorithms, or for some questions it'll be like I give you the framework or the skeleton of an algorithm, and you need to understand how to fill in the missing code in order to achieve some functions. Okay, so those are for the paper-based questions. And the second type of assignment is programming-based. Okay, I will upload Jupyter notebooks, and in that notebook there will be code skeletons or frameworks that you need to use in order to implement some of those algorithms that we mentioned in the lecture, or some new algorithms based on our slides content, okay, depending on which chapter we are in. Okay, and for Jupyter Notebooks, we use Python as the programming language. Okay, so it'll be great if you know Jupyter Notebooks or have used it before, but it's okay if you don't, because we're gonna have a brief tutorial next week for introducing, installing, running Jupyter Notebooks on your laptop computers. Okay. And there will be one midterm exam and one final exam. For those exams, all questions will be paper-based. Okay, and all exams will be in person in the classroom. Yeah, unless there's a future change in teaching mode or studying mode from the university. Yeah, otherwise we're gonna return to the classroom. Yeah, the exams are open textbook. Yeah, you can use PDF app. You can bring your laptop, but no Google, no wireless network allowed. Okay. Yeah. Okay. So yeah. So in lectures, we're gonna introduce a type of pseudocode to describe algorithms, and this pseudocode is follows the conventions of the textbook, and I think it's easy to understand, and it's semantic. And it's straightforward to capture the syntax, to understand the syntax. Okay, yeah. So that pseudocode will be the one that I encourage you to use for describing algorithms, whatever in paper-based assignments or in midterm exam or final exams. All right. Yeah, a little bit about me. So I'm a father of two kids. We live in San Diego, and these are a picture of my families, and we go hiking a lot. Okay. Yeah, professor or doctor would be fine if you want to call me or email me. Professor Xu, Dr. Xu, sounds a cool name. Okay, so for research, I do natural language processing, machine learning in general. And for this semester, I have another, I teach another course on Tuesday and Thursday morning, CS460 machine learning. And I'm interested in using machine learning methods to study human languages, cognitive sciences, and computational linguistics. Okay. So if you're interested, you can visit our lab's websites, and in there you can find most of our current recent publications and projects. Yeah, I see I received some emails. I want to quickly check if there are students who need the Zoom link. Okay, let's see. One. Okay. Let me quickly send the Zoom link to one of the students. There's another student. Okay. Yeah, hopefully they can join us in time. Yeah, the machine learning course is different from the speech processing course. Yeah. Okay. Yeah, that's pretty much what I want to bring up as an overview for this course. And I would like to answer your questions if you have any. And also, after this first lecture is done, I'm also willing to take questions. Okay, so let's why not just let us take step into the introduction parts, because it's also important. We will step into the question, dig into the rabbit hole of how and why, mostly why learning algorithms is important. Okay. Yeah, another thing I want to mention. So for these, the first 2 weeks course, the first 2 weeks classes, I will record the Zoom sessions and upload it to YouTube, and will be published the videos to the Canvas page. And for all the future lectures, I also requested the lecture to be recorded within the classroom. Yeah, I'm not sure. I didn't use that university service before, but hopefully we have good qualities of the lecture. Yeah. So yeah, so if that goes good, then technically we should have every lecture in this course recorded and available on YouTube. Okay, that's good to hear. All right, so yeah, let's see. When we talk about algorithms, what kind of concept or what kind of technique we are referring to? Okay, so if we turn to most of the textbooks, okay, I see another question. What is the attendance policy of the course? So I'm gonna talk about that after this part is done, and I will open the syllabus and cover some details about that. Okay. Yeah, so if we use most of the textbooks on the markets on algorithms, we can see that when we describe algorithms, we usually use a procedure or process that's between some inputs and some outputs. Okay, so we can say that it is such a procedure that processes some inputs and produces some certain outputs. This procedure is called an algorithm. Okay, so it is a tool that we use or we invent to solve any computational problems. Okay, all right, so you can see that it's the link, it's the map between the inputs and the outputs at a very abstract level. All right, okay, so if we take sorting problem as an example, okay, we know that it's a very typical, very common problems. Say, given a sequence of numbers, right? We have n numbers from A1 to AN, and we don't know their relative, what's the magnitude for each number is. We want to compare each pair of them, right? And the outputs we wish to obtain is actually a permutation of the original sequence, okay? Which means we change the orders of the same elements in the input sequence and get some outputs so that the outputs are in order, right? We want to reorder all the elements, right? In this example, we given the inputs from 31, 41, right, to 58, we want the numbers, the outputs, the elements in the output to be in order, okay? So whatever algorithms we use, whatever methods we use in between the inputs and the output sequence will be called an sorting algorithm, okay? So it's actually a quite straightforward concept to capture. Okay, but here we just said the procedures that can achieve such a goal, right? Well, we didn't even mention whether this procedure is performance or not, how fast it runs, right? But these are already the more advanced concepts or more advanced topics that we will cover in the next stage. Okay. Yeah, so before we care about the running time, how fast an algorithm can run, we actually need to first care about whether this is a correct one or not. Okay, so for a correct algorithm, whenever we change the input sequence, the inputs instances, it always halts with the correct outputs. Okay, so if we write an algorithm that we claim to sort the input sequence in ascending order, okay, and that algorithm will only be correct if it will output the correct sequence for every input sequence. Okay, although it's impossible to examine all the possible input sequences, but there's a way to prove the correctness of the algorithms. Okay, but as long as there is one input sequence for which the algorithm doesn't produce the correct outputs, then we will say this algorithm is not a correct one, okay, or incorrect algorithm. Okay. So we will say that a correct algorithm will solve the computational problem. Okay. And if an algorithm is incorrect, then it has some possibility to not at all. Okay, it will not stop at all, or it will correct. It'll halt with an incorrect output. Okay, so it seems trivial that's why we mentioned the incorrect algorithm here, because sometimes even if an algorithm is incorrect, it can be useful. Okay, as long as we can control the error rates, like we can make sure that maybe 99% of the chance the algorithm will produce and correct outputs, but maybe for that 1% it will give some errors, output some errors. If that is the case, then we need to consider the trade-offs. Okay, so if that algorithm is incorrect for 1% of the chance, but that algorithm is pretty fast or pretty efficient in terms of time or memory, then it's probably still a fair choice, a fairly good choice. Okay, yeah, depending on the performances. Okay, yeah, but for the primary interest or concern for this course, we will focus on correct algorithms. Okay, most of the problems that we will discuss are very deterministic. There's no deterministic. There's seldom some random or stochastic problems that we will talk about. All right. So next, let's see another question. Do we consider finding the shortest path correct? Yeah, for the shortest path problem for the graph, I think there will be correct and incorrect algorithm for it. Okay, it's still solvable within polynomial time. So if we're gonna when we introduce the concept of P and the NP and the NP complete, we will see that to find the shortest path in a graph with weights on different edges, it's actually a problem that's solvable in polynomial time and verifiable in non-polynomial time as well. Okay, but if we change it a little bit to say find the longest path, then it'll be a different case. Okay, but I wouldn't say it's not perfect. Yeah, well, we can keep discuss it later on or offline if you wish. Okay, but now let's look at more of the examples that we will probably go through within this course. Okay. Well, the first example is human genome projects. For example, we want to identify all the genes in human DNA and determine the sequences of 3 billion chemical base pairs, which is a very challenging task, right? But within that process, we need to explore algorithms that can efficiently compare, say, for example, efficiently compare the similarity or the distances between 2 segments of DNAs, for example. Okay, so that is an example of typical dynamic programming algorithms that we will introduce. Second, internet, right? In order to have the internet running, then we will need to have really smart algorithms to handle massive volumes of data. Okay, for example, the routing process, right? We want to find a good routes for each data packet. So we want to kind of prevent the longer paths between routers, and we want to receive the data packet as soon as possible, right? And for search engines like Google, it implements algorithms that are not only running fast, but also they can produce results that make sense, right? That semantically make sense. The more related content will be presented to you, for example. Okay. All right. And for electronic commerce, for example, and the recent hype of cryptography, NFTs, cryptocurrencies, algorithms behind are cryptography algorithms, which will basically based on the crypto hash functions. Okay, so these are I wouldn't say they are the most recent breakthroughs, but they do have very successful recent business applications, and they are actually the foundations of the decentralization technique or decentralization ecosystem in the recent era. Okay, so that is something we will touch a little bit about as well. Yeah, blockchain and cryptocurrency. Okay. Next page, we still have some other problems. Okay. So for example, here we mentioned the shortest path problem, right? It happens basically every day when you take out your phone to find the way to a destination, right? So it's actually a quite we have quite efficient implementations for finding the shortest route or shortest path problems already. Okay. Say if you think about the vertices, all those nodes or vertices in this graph as cities, okay, and the numbers between these arrows are the distance or the traveling time between 2 places or 2 cities, then it's a very well-designed or well-defined graph search problem, right? You want to find the shortest distance between the 2 vertices. Okay. So the longest common subsequence problem mentioned here is actually one algorithm that is suitable or maybe useful for the gene comparison tests or gene projects. Okay, because it's a problem that we want to compare the we can use to compare the similarity between two sequences. Okay. For example, say we have two ordered sequences, right? But with they may contain different elements. Oops. And we want to find the common subsequence between the two, but it has the longest length. Okay. In the example here, when we have x equals a, b, c, d, e, f, g, and y equals c, d, e, g, h, i, then the longest subsequence between the two will be c, d, e, and g, because c, d appears here, e is here, and g is here, right? And we cannot find any subsequences that's any longer. Okay, so it's a very typical example of applying dynamic programming algorithms. All right. Yeah, more examples, topological sorts. I'm gonna skip this really fast because we will dive into the details for these graph-based algorithms as well. Convex hull problem, it is also a problem that we can talk about near the end of the semester. It's a algorithm that we will apply the greedy algorithms sort of strategies, like a strategy that is similar to greedy algorithms. Okay. All right, so next, I have a very simple example here to showcase why we need to study algorithms. Okay, so what's the difference of writing two pieces of code? And maybe for the first one, we don't carefully consider the we don't carefully apply any algorithmic designs, but for a second, we consider the performances. We analyze the algorithm's performances really well, and we try our best to implement it in an efficient way. Yeah. So the reason of studying algorithm in one sentence will be that because we don't have infinite amount of time or infinite amount of computational resources. Okay, they may be fast, but we still have limited resource. Okay, and memories still cost you money, right? So as long as we have those bounded resources, then we need to consider using them in an efficient way. Okay. Let's see how the same problem can differ dramatically if we consider taking into the efficiency into consideration. Okay, let's simply consider the insertion sort and the merge sort. Okay, don't worry about it if you miss the details, if you don't remember it or haven't read about it before. But for here, we don't need to know about the detail. We just use them as the example to compare the performances. Say there's an algorithm called insertion sorts, and it takes C1 times n squared instructions to sort n items. Okay, so C1 is a constant. Okay, and n is integer numbers. And assume we have another sorting algorithm called merge sorts. It uses a different formula to compute the number of instructions needed. Okay, say it's C2 times n times logarithm of n. So this logarithm of n, we know that the logarithm have bases, right? We can have base 2 or base 10, right? So for here, it actually doesn't really matter that much. We can assume that it's base 2 logarithm function used here. Okay, let's compare how fast these two algorithms run, and assume that C1 is smaller than C2, which means the insertion sort is already at an advantage, right? And also, that means the faster we use a faster computer to run the insertion sort. Okay. Well, we assume that we run the insertion sort on a faster computer, which means more numbers of instructions can be executed within 1 second, right? Assume that computer A is super powerful and it can execute 10 billion instructions per second. Okay. And also assume that we implement it with a very powerful low-level programming language, very fast, and C1 is 2. Okay, this constant is a very small number. Okay, and then here we want to show a very extreme comparison. We assume that the computer that we use to run the merge sorts is a very slow one, an old computer. Okay, which means, for example, we assume that only 10 million instructions can be executed per second. And also we implement the algorithm with some not that efficient high-level programming language, okay? And which means we let C2 to be a much larger constant, 50 here. And we use very large input sequences to benchmark, to get a benchmark of the two algorithms. Say we sort 10 million numbers. Okay, so let's start the comparison, start the calculation here. Well, because computer A, it tells us that C1 equals 2, right? That's 2, and the input is 10 to the power 7, 10 million, 100 million numbers, right? Well, it's 10 million numbers. So according to the formula of the first algorithm, we need to use 2 times n squared, right? N is 10 to the power 7. So that's that number of instructions. And we know that computer A will execute 10 to the power 10 instruction per second. So we use the number to divide it by the 10 to the power 10 will give us the total number needed, the total time needed, right? Which is 20,000 seconds, which is actually 5.6 hours. That's already a long time we need to wait. Okay. All right, and we take the comparison with computer B. We have C2 equals 50, right? And the formula is n times logarithm of n. So we use 10 to the power of 7 times logarithm of 10 times of 7, right? If we use take a calculator, right, to divide it by the CPU execution speed, 10 to the power 7 here, then we will get only 1,163 seconds, right? Which is 17 times faster. Even the algorithm is executed on a slower computer, right? Even the algorithm is implemented with a much slower programming language. But since the algorithm itself is faster, since the functions that we use to calculate the running time here is a more advantage function, or a function that grows slower than the n squared function, then the ultimate the final output, the final running time outputs for computer B will be much faster than computer A. And this difference will increase when we sort even higher number of inputs. Okay. So now, as you can see, the importance for having more scientific, more better designs algorithms in solving the same problem. Okay, which saves us considerable amount of time. And if we analyze the same problem from the perspective of memory cost, we may also have similar results. Okay. All right. So, given the importance of algorithms, we can consider algorithm also as a technology, just like any computer hardwares. Okay. Not just the hardwares are necessary technologies, but also the algorithms. Okay. The performance of a computer system depends on efficient algorithms as much as fast hardware. Okay. And almost all the other CS technologies are directly or indirectly dependent on algorithms. Like when we design the architectures of computers, when we design the graphical user interfaces, when we design a programming language with object-oriented systems, okay? When we design the wireless networks, right? The routers, actually everything behind is an efficient implementation of algorithms. Okay. So to summarize, if we don't know much about algorithms, we may still be able to accomplish some tasks. But if we know some algorithms, or if we know how to build with good algorithms, then we can do much better, much more than knowing nothing about algorithms. All right. So from these slides on, we will review some mathematical backgrounds that may be needed, that are most likely needed in this course. So I would recommend you to go through the slides carefully yourself. And also these slides are something you can keep for references when we have encountered future chapters and assignments questions. I believe these equations introduced here will be useful for you to solve future problems. Okay. So we'll start from the basics, okay? So first of all, the floor symbol, okay? This is quite commonly used. We use floor of some real number or float number to indicate the largest integer that is less than or equal to x. Okay, this is a quite common operations, right? The floor over 2.9 is 2, and we may have also need to use this in our Python implemented assignments. Okay, in Python, there are multiple ways of accomplishing this floor operations. And ceiling is also another thing that gets the smallest integer that's greater than or equal to x, right? Okay, that's the first concept. Second, the modular arithmetic. Okay, so it's also a basic arithmetic operations. So modular means that when we are divide one integer with another positive integer, then the remainder or the residual of the division will be written as like a mod n. Okay. So it's basically a minus the n times the quotient, right? Which is the floor of the floating number a divided by n. Okay. So the mod operator is also implemented in most programming languages, including Python in this case. Okay, and it's a simple operation, but we will use it for as the building bricks for more complex hashing functions, for example, in the hash table. And also it's very common, very widely used in different types of hashing or indexing technologies. And there's a concept called modular equal, okay, as the equation here indicates. If A mod n equals B mod n, and we will use 3 bars A equals B with mod n within the parentheses to indicate that they are equal, A and B are equal modulo n. Well, this is just a fancy concept, but the nature behind it is just the modular computation. Okay. And exponentials. Okay, so exponentials is also something that we will come into across a lot for analyzing the algorithms. Okay. So for all real numbers, all positive real numbers, a, m, and n, we have the following. Okay, right? A to the power of 0 and 1, -1, right? And a to the power of n and an n, right? These are the principles for exponential computations. And we should know that the function, exponential function, a to the power n, is a monotonically increasing function. Okay. And it can be, actually, it can be used to use such a exponential function to indicate the natural logarithm function space. Okay, how we define the e to the power of x is to let 1 plus x power divided by 2 explanation, right? This means the 2 times 1, right? And the 3 exclamation means 3 times 2 times 1. Okay. So we will review these concepts in the next slide, where the explanation is the factorials function. Okay. And we also have, if we let n to be really big numbers, then 1 plus x over n to the power n will equalize will be equal to the e to the power x functions. Okay. So it doesn't mean that we have to fully understand why these equations are valid, but it may be useful for some of the proofs in one of those, several of those theorems that we will need to learn about divide and conquer algorithms. Okay. Yeah, and related to the potential exponentials is the logarithm functions. So logarithm functions is something we will come into across more often than the exponential function. Okay, as we already seen that we use the n times logarithm of n to describe the efficiency of the merge sort function, right? So as I said here, log function, we need to define the base, right? If we write the b in the subscripts, log subscript b of x means that we compute the log with base b of x, right? And so that's the y. So the value of this value of this function y, right, is satisfy this equation. B to the power y will equal x. Okay. And the logarithm function is also a strictly increasing function. Okay. Whenever we have a larger input, the output will always be larger. And the logarithm of 1 equals 0. And the logarithm of a product can be decomposed into the summation of 2 logarithms. And the logarithm of a exponential term, we can remove the exponential a and make it outside the logarithm function. Okay. So for logarithm, for the short term of logarithm base 2, we can use LG for more brief notations, right? And logarithm of E can be written of Ln. But in this case, we will usually use LG as the most common usage. Okay. So next, this property, the logarithm base B of A can be converted to log base C of A divided by log log base C of B is called the so-called switch base theorem. It's an interesting property that we can use in some of those proofs. And the a to the power of logarithm base B of C is something we can switch the a and the c, and we have the equation still valid. Okay. All right. And then we come to the factorials. Okay. So the factorials, as we said in 2 slides ago, we said that the 2 explanation, right, is 2 times 1, right? But we have a more general recursive definitions here. Okay. Other than defining n explanation equals 1 times 2 times 3 times n minus 1 times n, we can use a recursive definition of this factorial function like this. Okay. So we can define f of x as an explanation, right? So this explanation, this factorial of n is actually n times the factorial of n minus 1 factorial, right? So we can write this internal term as f x minus 1. Okay. And if we hit the boundary, if we hit the recursive or recursion boundary when n equals 0, then we define it as 1. Okay, so this is the first occurrence, the first mentioning of the recursive definitions. And for divide and conquer algorithms, we will have a lot of recursions or recursive definitions in such a form or in similar form. Okay, and permutations and combinations, I hope you can go through the mathematical details yourself, and I'm not going to cover the details. These are just mathematical formulas here. Combinations, yeah, related to permutations, K permutations. And summations, yeah, this is something we will need to use in proving the master theorems of divide and conquer algorithms, divide and conquer solutions. So the summation of arithmetic series, right, which is easy to memorize, right? And the summation of squares and cubes, you don't need to memory of it, memorize everything here, but they can be useful in the future lectures. And another important series is the geometric series. Say you add 1 plus k to k squared to k to the power of n. So for computing this geometric series, we also have formulas, right? We can use n to the power of n plus 1 minus 1 divided by x minus 1. So this has an interesting property because we have x to the power of a very large number here. So x, if x is between 0 and 1, if it's lower than 1, then this will have a limit that's approaching to 0, right? Right, when x is always, when x is smaller than 1, then the solution for this geometric series will be a constant like this. All right. And for harmonic series, we maybe use it sometime in the future, but not necessarily so. The interesting part is that the function is grows as fast as a logarithm of n function. Okay, and we know that the shape of a logarithm function uh, almost looks like this, right? It grows faster when it's near the zero, right? When it has small numbers, it's small inputs, but it grows slower and slower in the larger input area. Okay, so logarithm function is actually a very friendly function to algorithm designers. Yeah, if we can find the solution that runs in the logarithm time, then it's actually a very good solution. Yeah, and for integrating and differentiating series, I will leave it to yourself for the after class reading, and it will basically to differentiate both sides of the geometric series, and you can get why we can infer from the left to the right in this case. All right, so that's pretty much for the first introduction slides. We had a quick going through of the mathematical background that will be useful in the course. And I wish you can spend some time reading the slides. And also there will be a related chapter in the book that covers the mathematical reviews. And let's going back to the syllabus. Let me open up the syllabus page. Oops. Syllabus. All right. Yeah. If you have questions, let me know by now. So right now the class is already full, and the university have very strict requirements on the maximum number of students allowed in a classroom. So I don't think I'm able to add more students to the class right now. Really sorry about that. And where can we see the recommended reading? So I will place a recommended reading message at the beginning of each module on the Canvas page. Okay. So say next week we're gonna have officially starts the examples of insertion sort and merge sorts. Then I will put the page ranges for you to read on the Canvas. Okay, from page 16 to 29, something like that. Yeah. All right, so we will meet online on Zoom for the first 2 weeks, and but for future we'll go to Music 245, and we will have that in classroom records going on as well. Okay, office hour Thursday 9 to 10. for the Eddie's question, sorry, you can assume that the class is completely full. Yeah. Okay. So for assignments, you see, what I planned here is that we have 5 question sets and 5 programming assignments. Yeah, so for programming assignments, there could be multiple Jupyter notebooks. Okay, so I put only one question set and one programming number 2 here, but that doesn't mean that there's only one one notebook for the week from 3 to 5. Actually, there will be multiple questions. And we will have our first midterm exam on March the 24th, right before the spring recess. And our final will be on May the 10th. Yeah. So for midterm, it'll be shorter. Okay, it'll be an in class, so it'll be 75 minutes. So we will have we will have 25% on paper-based assignments, 25% weight on programming-based. So in total, that's 50%. And the midterm takes 15%. Final takes 30%. Yeah, for the finals weight, I'm still considering it. It may be too high. Yeah, I'm thinking about moving 5% off to midterm or to the programming-based assignments. So for the question sets and the programming Jupyter notebooks, I usually upload them after the class. It usually is after the Thursday's class when we talk about when we start for example, when we start divide and conquer. Well, when we start the 2 examples getting started, then I will upload the questions on Thursday. Yeah, but for example, for common sorting algorithms, heap sort, quick sorts, there will be more than one Jupyter notebooks. So for the assignments, for the programming assignments, it's likely that I will put a Google Drive, a link to Canvas, and in that link, in that folder, I will continuously update the contents. Like I can add into that folder with the new Jupyter notebooks. Yeah. Yeah, this is the first time I'm experimenting this with programming-based assignments because I think it's useful. It's helpful for you to understand the algorithms and for you to practice algorithm programming skills as well. Thank you to Matthew for creating the Discord server. So do a suggestion, go 5% to programming because we have more time to do that. Yeah, sounds reasonable. Okay. So if you need to reach me, please use my email. Okay. I found it's easier to use email rather than using the direct message on Canvas. Okay. Are there any other questions? What is the attendance policy? Oh, yeah, attendance policy. So my purpose of using the 5% quiz questions is that I do wish to appear in the classroom. Okay. So I will use that quiz question as an examination of how many people are there. For the recording, I will first upload the Zoom recorded video to my YouTube channel, and I will place the YouTube link under each module for each under the slides for each module. Yeah, it'll be a different link in there. Class excuse letter. Yeah, so if you missed class because of COVID-19, you should let me know. And by first sending emails to this email address and get the class excuse letter. Add some letters. Hmm. All right. So that's so much for the syllabi. Wondering if you have other questions. All right, looks like there's no other questions. Oh, thank you. I'm gonna record. This part link doesn't work. So bad. Yeah, hopefully you can figure that out. And then you can also use Canvas to use the discussion panel to post any information about this board. Okay. Yeah, you can say the question to me. Thank you. Bye-bye.
Okay. So okay if can you hear me, Professor?
Yeah.
Okay. So as far as the quiz go, because for my accommodations, I have well, for my accommodations, I'm not going to mention it. So the quiz questions are usually pretty straightforward.
Yeah.
Okay. Because for my DSS accommodations, I have a time and a half. That's what I was wondering
Mhm.
if that applies to the quiz itself as well.
Yeah. So as I said, so usually the quiz questions are straightforward examinations of what's going on in the class.
Hmm.
And as long as you submit it with your name, like on a piece of paper with a name on it, then I will give full credits.
Okay.
Yeah, it's kind of a different form of attendance check.
Oh, is it like a time, like a regular exam?
It's not a regular exam.
Oh, okay.
No,
Okay.
it's not. It's
Okay.
occasional.
All right. Sorry, I got a little bit confused how it worked. Thank you.
No
All
problem.
right, have a good one, Professor.
You too. Bye bye.
Bye-bye.